about lymphocytes. They come in the two flavors, the B's and the T's. And they are going to be recognizing a very specific agent, and not just the whole agent, a very tiny, tiny portion of a bit of a thing off of that agent. And so what are the antigenic things, the thing which looks foreign, the antigen, is typically something from the surface of that virus or bacterium. And so when we generate, which makes sense, because that would be the thing that would be seen by the immune system. And so when we generate vaccines, they're often antigen that would come from that surface of that thing. And so an antigen is the thing that appears foreign, antigen, and it has some real basic requirements. That for the lymphocyte to recognize it, it has to be specific to that antigen. The immune response has memory for that antigen. This is why we want to create immunity by vaccination. We'll show it to you so you can have immunity before you encounter the real thing, which might make you sick. So memory is a very important part of specific immunity. And then tolerance of self, which is, you know, it can be a trick. And so you certainly have discussed autoimmunity when that tolerance of self goes wrong. And so often what really happens is we have a response to an antigen, but there is cross-reactivity to a self-tissue. It's less common for the body just to become intolerant of self-tissue without some sort of link there that had created an immune response in the first place. So this is true about the specific immunity. So antigens are the thing that would induce that response. It has to be recognized as foreign. It is immunogenic. It would induce and it would elicit an immune response. Typically, they have to be big enough to be kind of seen, and typically they are an antigen would then be a protein in nature. So while a chemical or particle may be phagocytized, it isn't always going to have antigenic properties. So phagocytes are only phagocytizing things that bear antigens. And so phagocytosis happens, antigens are specific to immunity. And you have to have that antigen have shown up, always remember, it has to show up by the right route of transmission. It can't just be something that's on the skin. It has to be inhaled, maybe, or whatever its appropriate dose route is, and also in a dose that would be stimulatory to the immune system. And so I often think about it this way. So you have been vaccinated against chickenpox virus. So if you encounter someone with chickenpox, that doesn't mean that that virus may not come onto your body, enter, and begin to replicate itself. It would. You would just be able to eradicate it before you had even prodromal symptoms. You wouldn't have to have symptoms because the immune response, the memory to a prior infection is huge. That response is very big. So I think this is where it's important to just be cautious generally. So even though you've had, so say that, you know, there's someone with chickenpox, you see that person, this is where you're going to encounter a lot of these agents. And you think about, I still can go home or go to my next patient and kind of carry that agent there. And so I want you to always think about, you know, that's why you got, it's not, you know, wash your hands and all that stuff, but think about, man, am I going to go to the nursing home? I was just at so-and-so's house, you know. I mean, you have to think about these things, that immunity is, it works, but it doesn't mean the agent isn't like getting there as well. And I don't want you to be, freak out all the time about what's on you. It's just that it works. The whole thing really works. And we have this herd immunity because a lot of people have been exposed as well. So that's a good thing. The fewer people that get vaccinations, there is a decrease in herd immunity. So you can be a few people without vaccinations. We're all vaccinated, and that means the organism isn't really taking up residence in us very well and will protect these few. When this number gets big enough, you start to see that disease becoming, the herd immunity doesn't cover them anymore. Do you see what I'm saying? So that's what is happening, and we're seeing a lot higher incidence of certain diseases. I'm for vaccination. I'm not against it. But you kind of have to respect if someone's making a very educated decision for themselves to do that. But anyway, antigens, antigen presentation, that's the big deal. That's what phagocytes are going to do. They ingest the foreign thing. They take some of these particles and they will present them. And how they do that is because they will have a cell surface receptor. So cells are going to interact with other cells. And how do they do that? They do that via receptors on their cell surface. So the phagocytes are going to have cell surface receptors that will have the antigen there, and that you can go up and show it to other cells. Antigen presentation. And so phagocytes that are antigen-presenting cells are monocytes, macrophage, neutrophil, and T helper cells. And really any white blood cell can act as a phagocyte. They'll place the antigenic determinant. And when I say determinant, so you have an antigen, which is just, say, a protein that was on the bacterial cell surface. An antigenic determinant will be a tiny portion of that, maybe 6, 9 amino acids. That protein might have been 300 amino acids. So an antigenic determinant is just a little tiny piece of that. That's how specific it is. And that big protein will have had several antigenic determinants on it, and we can recognize them all. It's an unbelievable, limitless system of ability to recognize antigens. It's unbelievable. I still don't get it. So, lots of words here. The antibody or T cell receptor. Okay, so there's a receptor on the antigen-presenting cell, and there's a receptor on this lymphocyte. Depending on which this lymphocyte is, this receptor will have a different name. If this is a B cell that makes antibodies, then this receptor is going to be an antibody, also known as an immunoglobulin. If this lymphocyte's a T cell, then this receptor is going to have the name T cell receptor. So lymphocytes have receptors that recognize antigens. The antibody would be on a B cell, T cell receptor would be on the T cell. That's a really good name. It doesn't interact with the entire antigen, only these little bits are antigenic determinants. It is the lymphocyte can be stimulated by being interacting with the antigen at large, but it's really going to be best if it sees it in the presence of the antigen-presenting cell. So antigen presentation, therefore, phagocytosis is the most important step in initiating the immune response. So really, when you look at these different factors for defense, they really do go in this order. Just the physical-chemical barriers, if they get breached, then you have non-specific immunity, which is very much going to be about phagocytosis. And then phagocytes can present specific antigens to B cells and initiate specific immunity. And there are two branches for specific immunity. Humoral, which is B cell, and B cells make antibody. And then there's cellular or cell-mediated, which is T cell. And they send out cells to do the work. That's why it's called cellular. Humoral comes from the humor, which is the blood, and so this is immunity that's out in blood, sort of form of an antibody. Antigen presentation, so here's how it goes. The B cell receptor is its surface antibody. The T cell receptor is called the T cell antibody. So those are the lymphocytes. The receptors are pretty similar. A T cell receptor looks a good bit like the B cell receptor. So they all have something like this kind of format. This would be attached to the cell surface here. They have heavy chains and light chains. And they have constant regions and variable regions. So that every antibody or T cell receptor would have its heavy region would look the same, or constant region would look the same. It's the variable region that's different. First, the variety, so that you can recognize all the different antigens. It's in that variable region. So anyway, they're going to be pretty similar to this. The one on the B cell, the one on the T cell. Recognize these antigens. And it has these arms. And this is, you know, you always see them like goalposts or YMCA, you know, but it really is something that's going to be much more of a glove that can fit that antigen into it neatly and snugly. Like you would, you know, you would imagine something in your life being much more intimate of a relationship. So antigen presentation. So the receptor on the antigen presenting cell has a name as well, and it's going to be part of the major histocompatibility complex. We call it the MHC molecule. So here's the antigen presenting cell. It's a phagocyte. It's a monocyte, macrophage, neutrophil. Maybe it's a T cell, any sort of phagocyte, and it will have the antigen. It will hold antigenic determinants on its MHC molecule. The lymphocyte will interact with that antigen at the level of that, right there, like that. TCRs, T cell receptors, specifically bind peptide antigens presented by MHC molecules. So the MHC is a platform for antigen presentation. A chaperone. So MHC molecules bind to both T cell receptors and a co-receptor called a CD. That stands for cluster of differentiation. And so, think of it this way. This is a T cell. The T cell receptor is here. It recognizes the antigen. The cluster of differentiation molecule, CD molecule, recognizes the MHC. So that you just have a way to fit both things in there. So that's not so complicated. Now, there will be two flavors that MHC molecules come in, and there will be two concomitant flavors that CD molecules come in. Now, there are a whole bunch more, or you wouldn't see the number 4 or 8. There are lots more, and there will be so much more information coming out during your practices. This is one reason why you have to get continuing medical education. It won't matter a lot to you unless you're in, doing cancer, hematology kind of stuff overall. But there are several, they appear on different cells in different lifetimes and different iterations of those cells. The ones that we really care about a lot would be a T lymphocyte CD8 or a T lymphocyte CD4 molecule. And you just get this recognition. The CD molecule plugs into the MHC. The MHC is presenting antigen, and that receptor will just recognize the antigen. That's all. But it becomes important, not so much to visualize it, but really in how the whole thing functions, and that you have a differing distribution of MHCs and CDs. So MHC class 1. So I said MHCs come in two flavors. One is class 1. So this is called major histocompatibility complex because it's really being named from the standpoint of the DNA and not the molecule itself so much. So there is a big locus of information on the DNA that relates to this histocompatibility. And all of these things were kind of defined originally based on tissue typing. So HLA, MHC, all of that was really about kind of cross-typing to get tissues to not be rejected. So if you're histocompatibility, if you're histocompatible, then this tissue that gets transplanted won't be rejected. So does that make a little more sense where it all kind of came from? So that's why these words sound so particularly weird, I think. It sounds random to me, cluster of differentiation, and HLA and MHC and all that. It really comes from tissue typing because we knew more about that and rejection and cared about that before we knew about how the immune function happened. So anyway, that's why those names are weird. MHC class 1 molecules are found on all nucleated cells. And so that's really interesting. So any cell can perch a little something on its MHC molecule and say, so I'm in trouble. I'm in trouble. You know, like, you know, someone is right behind you and you want to take all your money out of the bank and you stand there and go, that's what the MHC1 is doing. And so what can come by would just be some flavors of cellular T cells or something like that that can come and just get rid of that cell. Kill a host cell. Sacrifice a host cell for the greater good of the cells surrounding it. And so that will be recognized specifically by T cells that bear the CD8. So remember, this T cell receptor would recognize any antigen, but it won't necessarily recognize any MH molecule. So a CD8 likes the flavor MH1. This is true. And this is really great against an intracellular kind of pathogen. That would be a virus or some certain intracellular bacterial organisms. They need gonorrhea, Rocky Mountain spotted fever, chlamydia, plasmodium, the malaria, those kind of organisms that stay inside cells. That cell will look different because organisms will have placed, or parts have been placed on MHC1 molecules, and then the T cells are just going around looking like they're like the Secret Service looking for someone bearing something that doesn't look right, and then they can come up and take that cell out. Cell-to-cell combat. Okay. Now that MHC class 1 is really several flavors of HLAs, or human leukocyte antigen, human lymphocyte, I think it's lymphocyte antigen. But that HLA was that tissue typing, those tissue typing flavors. So anyway, so MHC class 1 is really representing a lot of different molecules. But the main thing about it is it's just on nucleated cells, and if there's something wrong inside that cell, it is that MHC1 that can be locked onto by the CD8, and the cell will be killed. Oh, okay, got that? Did you get all that? Wow. And those pictures don't really relate to that. They're better on this slide than relate to this slide. The class 2 molecules, now those are going to be really specific to immune defense and all of that. So MHC class 2 molecules will be really specifically found on antigen-presenting cells and B cells as well. So all antigen-presenting cells will be will have MHC class 2. So if this is an antigen-presenting cell, this has to be an MHC class 2 molecule. T cell receptor is the same. This is a T lymphocyte, and this is the T cell receptor. And so this CD molecule will be a number 4. Gosh, I just love the way I fold that in with 2 different colors. Yay me. So anyway, it's just all it is a way to say, look, here's the antigen, and then to have kind of a way to lock in so that can happen. And why would you need this CD thing, and why do you need a co-receptor, and all that seems kind of wacky? But it makes sense. You can't just go, do you know this guy? And hope that that happened. So if you have this way of locking this T cell onto this MHC receptor, then you're forcing it to look at this antigen. It just helps increase a lock. Because otherwise you don't want these cells to lock permanently. It's just an attraction. So we need to be able to kind of hold that attraction for a little while, and that cluster of differentiation chaperone will help that happen. No, I said look at it. Look at it. Do you know staph? This part of the staph organism, and the T cell can go, oh, I do, ah, and go get excited, react. So it kind of makes sense. It's creating just a little moment. It's just a moment between those two cells. Okay. I don't know that it's Facebook official, but it's a moment. Is that a thing? I know my son-in-law changed his Facebook thing that he got married. I don't know. I thought that was really cute. I mean, it was because he married my daughter. If he got married to someone else, it'd been really good. There'd be a homicide in Texas. So anyway, all you have to know is MHC2 is on an antigen-presenting cell, and it will be presenting to a T cell with a CD4. And then it all gets going. So let's look at this, how this works. Cell-mediated immunity, or this cellular branch of specific immunity, is the one that T cells engage in. And so when we talk about or think about immunity, we're really thinking very much about antibodies, antibody titer, immunoglobulin, and that's only half or less than half of all of the immune response that really happens. T cells are the pivotal moment for everything happening. B cells wouldn't even get hot and bothered if it were not for the stimulation of a T cell. And so T cells are really super important. And we didn't really care very much about T cell immunity. You know, it was there and we learned about it and whatever. But until HIV, because HIV is specifically destroying population of T cells, the helper cells mainly, and changing immunity. So if not for HIV, all of the information that we're just having about the immune response would never have happened. And all that implies. I mean, it's just really changed everything. Allergy is all about inflammation and immune response and all of that. So anyway, something bad happened, and it made us all much more knowledgeable. I hope we can apply that always. Particularly, cell-mediated immunity has its efficacy toward intracellular pathogens, funguses, and parasites. Really good because these cells interact directly and can kill the cell that it recognizes as foreign. So it's really good for these things. And so when you see T cell dysfunction, you really do see more of those kind of illnesses. B cells are going to be really good against bacterial infections and also viruses. So what you really do, you have these two arms that have effectivity in a broad sense across all the different kinds of foreign things. T cells also are against transplanted tissue. So there are several populations of T cells. We'll talk about some of the biggies. The T helper cells, the little sub H stands for helper, and they will bear the CD4 molecule there, recognizing MH2. They are activated by antigen-presenting cells in conjunction with that MH2 plus its specific recognizable antigenic determinants born on that molecule. So what happens is, okay, so the T cell is sitting there in lymphoid tissue, galt, malt, lymph node, wherever it is. The T cell is sitting there, and the antigen that it recognizes is presented by an antigen-presenting cell, and then it gets stimulated to enlarge, mature, proliferate into many, many clones of itself. So if you could take a special operations Marine, and it has a specific tactical duty, and you could clone that Marine into hundreds of thousands of like Marines, you would have soldiers dedicated to killing one opponent. And that's very effective, and that's exactly what happens. So the immune response gets elicited this way. Then you'll have a few T cells that understand or recognize that antigen sitting, waiting in lymph nodes your whole life. You're born with that sense of recognition. Isn't that insane? That you're born with the ability to recognize shit you've never seen? And this is amazing. And this is one of the reasons our DNA is so valuable, you know, for the way we live our lives. And the way this animal lives on the planet Earth. So a couple of subsets can emerge from that T helper class, of course. There are going to be several. There's so many cells, and there's so much research out there. They all have different markers on them, and it's really messy seeming, but what you're really trying to do is to create an explosive reaction to something so you can mount a good, strong, specific attack and eradicate it. A type 1 kind of T helper cell is really going to it's really going to be good at killing enhancing the killing efficiency of macrophages. So see how they go. No, you go. No, you go. You do it. No, you're the best. No, you're the best. I love your hair. No, I love your hair. It's like that. And they just get each other so geeked up, and they go into battle like, assume the stance and go into battle. They just get each other going. So there's this self-aggrandizement within the group. God, it's just exactly like politics right now, isn't it? Probably always has been. And then the type 2 will go over and can really work on the B cells. So you stimulate the T cell, and the T cell will stimulate more antigen-presenting cells and B cells. So you see that the T cells really can make that reaction to an antigen just massive. So Staph aureus crosses the barriers. It has a lot of virulence factors. It's kind of, it's got its tactical gear on. It's a badass. And so then you have the antigen-presenting cells are eating them as fast as they can, trying to get rid of them, but also going, help, help, have you seen it? Do you know? And I got it. And then, and they go and eradicate that Staph aureus. Unless it's such a great Staph aureus, it can evade. It can just, it has more weapons than you do. Which happens. Okay, T helper cells. There are also T cytotoxic cells. And these cells will be really good at specifically then going to the thing that was bearing the antigen. So the T helper cells are like going, oh, you help, come on. And the T cytotoxic cells will go up and go, like I got this. And they'll go do the hand-to-hand marine combat. And so they're called cytotoxic. And what they really do, they can go up and recognize cells and just kill them where they sit in situ. That's why it's called cellular immunity. Those cells will exit lymph nodes and go to the source. They are dropped out of a helicopter right to the source. So when stimulated, they circulate and kill antigen-bearing cells, antigen-specific recognition. So how do they do that? They are degranulating. They are releasing tons of proteins that will insert and poke holes in that foreign cell, or that transplanted cell, or that cell that is infected with an intracellular pathogen. They'll kill the cell that's bearing that antigen directly by poking holes in it. So there's a bunch showing you a release of all of the contents, and that cell dies. There are also a subset of T cells that will get excited by a specific antigen that are known as suppressor cells. A subset of them will also bear the CD8 marker, but they will inhibit the T helper cells. So as much as you spin, you gin up all of this activity, you have some T helper cells going, yeah, stop. Because you need to, you don't want to spin your wheels. Once you've begun to eradicate the foreign source, you don't need these numbers still growing. So you have cells that will recognize and kind of downplay that. So sort of stamp out fires. Then, very important that you have those. We used to call some of these T suppressor or T cytotoxic cells, we used to call them T natural killer cells. There's a little overlap, but there are cells that are just called natural killer cells. And some of them look like T cells. So there's several populations of natural killer cells. Some of them are also T cells. But they don't require stimulation. They just recognize they're not really part of all of that. They can just go up to a cell that looks foreign or different and kill it. They are mercenaries. They don't associate with any uniformed corps. Now there are a subset of T cells that look like that as well. So you see there's a lot of cells to make this happen. So good is our ability. But then you also think that that's going on. While that's going on, while you're mounting this immune response, you're in the acute phase of the illness, and your body just even mounting an immune response makes you not feel so great. You know? And so so that's why people are ill, and that's where that decline in convalescence is slowed, because your body has climbed a mountain cellularly. You know, and so that's why rest, and you've got to make sure that they get nutrients, all the things you need all the time. Nutrients, good quality protein, rest, water. Humoral immunity, or that B cell branch of immunity, then, that's the antibodies. We know a lot about antibodies and love them, but just remember, T cells are for amping it all up, killing hand to hand, and also for downplaying. B cells will interact with antigen and also antigen presentation to get geeked up. It actually takes them a little longer to get geeked up, because to really stimulate B cell response and antibody production, you really had to get T cells stimulated to do that. And so you see that there's going to be a tick slower in getting B cells going. Branch immune system mediated by B lymphocytes, B lymphs, B lymphocyte, B cell. That's all the same word. Activated B cells produce antibody, and that circulates. So the B cell will sit there in the lymph tissue, and it's the antibody itself alone that goes and circulates. So that's why it's called humoral, whereas with T cells, T cytotoxic cells, they are actually, the cell itself leaves the lymph node and circulates. So that's cellular immunity, and so antibody only is called humoral immunity. Humoral immunity is specifically effective against bacterial pathogens and viruses. So T cell is really good against other. And really, it's T cells and natural killer cells that are going to go around and recognize cancer cells. I mean, and B cells will produce antibody to cancer cells as well, but obviously because you do treat cancer with monoclonal antibody, but it's the T immunity that can recognize cells that have transformed. So they haven't been infected by something, but they no longer look like themselves, and so it's no longer tolerated, and then you can mount an immune response against it. Immunoglobulin structure, really this is very much like T cell receptor structures, that you have this kind of heavy chains and light chains, and then these areas that recognize the antigen. So that's the basic immunoglobulin structure. The variable region will recognize the antigen. So we have about 5 flavors of antibodies. Immunoglobulin G, gamma, IgG, immunoglobulin gamma. The word immunoglobulin is the same word as the antibody. So you'll hear them used interchangeably. And it's A, capital A, little b, or capital I, little g. Gamma, 80% of circulating antibody. So when you look at blood proteins, albumin is first, and immunoglobulins is in there about number 3, I think. But of those immunoglobulins, 80% of it will be in immunoglobulin G. So that's really the main one. It's the second one that appears in immune response. And it's also produced by memory cells. So we'll kind of get to that. IgG can cross the placenta. And so when you're born with innate immunity that's maternal IgG that has crossed the placenta and entered the neonatal bloodstream across that has been absorbed across that placenta. And so when you're born, your mother's circulating, maternal circulating antibody should last as long as any antibody should last in the bloodstream. And so that's going to be, months, 4 to 6 months, something like that. And then that's about the time that the neonatal immune response will begin to happen. And you just start to have cells, even if they haven't been stimulated before, they will have a very low level production of their own antibody. It will be a very high production of antibody once stimulated. So that's why you have a titer at any given time, is because B cells will make just a little dab. Immunoglobulin M. So look at G. It's a monomer of the classic antibody structure. Immunoglobulin M is a pentamer, or 5 of those. So it's a honking molecule. Do you think anything that big could cross the placenta? It can't. And so it's joined by these little molecules called the J chain, or join. 5 to 10% of circulating antibody is the first to appear in immunoglobulin response, or immune response. B cells will first make IgM when they initially get stimulated to make antibody, so that you can just spit these big honking molecules out there to do some good. Then that B cell will switch classes and begin to make IgG. And that's what I mean by immunoglobulin switch. They won't go back to making IgM. They will stick with IgG at that point, including once the threat has been eradicated and you have memory cells that remember having been responded or having been stimulated before, and they'll make IgG. And look, T cell activity will cause the switch. And the amplitude will increase. There is IgA, 10% of circulating antibody. It's found in secretions, so breast milk, tears, sweat, IgA. But it will be found a lot in mucus. So in the mucous membranes, IgA producing cells will really live in those patches, or that malt or galt, the mucous membrane associated lymphatic tissue. Yeah, that's really where a lot of IgA will be made. Did I say breast milk? IgA will be secreted in breast milk, sweat, tears. And so not as much of it will be circulating. And look, it's a dimer. There is IgE. IgE. We have lots of IgE because IgE is the thing that really recognizes allergens. So that would be associated with ingestion, inhalation, and skin contact. So again, these things will be associated with mucous membranes. IgE will bind to mast cells and basophils. That's another kind of white blood cell. When the IgE, which is sitting there as a cell surface receptor for those white blood cells, encounters the antigen or allergen, you have degranulation of those cells, a lot of histamine, so it increases permeability and all the things you think of as allergic. Runny nose, swelling and itching, pruritus in the skin, gastrointestinal complaint, diarrhea kind of stuff. So it's responsible for the allergic response. IgD is probably the actual immune, very little is circulating, but it's probably the actual class that's sitting there as the receptor on a B cell. So the B cell will then go make IgA and B whatever. Antibody production. Okay, first, how does it ever happen? First, there's exposure to the antigen. The B cell can bind the antigen via its surface immunoglobulin, which is probably the IgD, and it can get excited. And or it's a co-presentation with an antigen-presenting cell. Which one comes first depends on if you're the biologist that likes B cells or the biologist that likes phagocytes. So you see kind of differing aspects of the perceptions of the same thing. That antigen can be presented on MHC to T helper cells and stimulate the co-stimulation kind of thing. So an immature B cell can be stimulated directly by antigen, but you have a better stimulation if it's either with regard to an antigen presenting cell and or a T helper cell. T helper cells can act as antigen presenting cells to B cells. Recruitment, excitement, yo! And if that seems just weird, don't let it bug you. They're all white blood cells. Phagocytes are white blood cells, lymphocytes are white blood cells. They can all stimulate each other because we want to get the thing going. T helper cells are super pivotal in stimulating B cells. And so what happens? It gets excited. It's going to make the T cells secreting stuff to excite it. Phagocytes excrete stuff to excite it. It gets excited. Its DNA will be amped. The transcription, not DNA, but the transcription will be amped, and it will just sit there and start to make antibodies. It'll make IgM flavor first, and then eventually it will just be making the IgG flavor. And it can produce something like 2,000 antibodies a second, which is inconceivable to me. When you think about, remember, transcription and translation, and then all the ATP to keep that going. So do you see I say it's a big cell that sits there in the lymph system and just does its job? It does. It swells up, it gets bigger, and also they proliferate and make clones. So it's not enough to make one cell excited, you have to do that, but that cell will undergo mitosis so that you have clones, that you have multiples, just like with the T cell. Lots of clones or soldiers that will recognize that exact antibody or antigen. B cells do the same thing. B cells will get big and actually be called plasma cells once they're excited. And then you have lymph nodes. So think about when you have, and you've all had lymphadenopathy, some of you have it right now. Sometimes I have one node that just stays kind of big. You may be able to see it right there. But why do your nodes get enlarged? Because you've created T cell clones and B cell clones, and you've gone in number of clones. That's not a bad thing, you know? They get bigger because it's working. But what it does tell you is that there is a nascent infection. And so that's why you're looking for them. And that edematous enlarged node is tender. So it's not necessarily a bad thing, it's a sign of a thing. Now, sometimes those nodes don't drain so well when they have a lot of cellular activity in them because of all the monoclonal expansion. They don't drain well and they get edematous and particularly tender. And so people don't like it, but it is a sign that things are getting better when the nodes are starting to get small. And with decreased drainage, they'll remain large. So, big nodes hurt. There you go. There's a pearl. Those big nodes, but they hurt. I don't know why that's funny to me. I'm dumb. So, and then that B cell, that immature B cell, got excited because T cell and antigen and everything was getting excited, and it got big, it became a plasma cell, it made lots of clones, it made millions of antibodies. Those antibodies did their thing, it worked. Now this cell can just become quiescent again, but it remembers, oh, I remember what happened last time. And it will be a memory cell, and it will continue to secrete IgG at a low level. That's why you have titer to everything you've been infected with before. And that memory cell, it doesn't need very much stimulation. Once it recognizes, it will clonally expand again and make a ton of antibody. So look at over time. The antigen is injected in the primary response. The first time you engage naturally or artificially that antigen, you get this IgM is being made, and then a class switch occurs and IgG gets made. Then that titer will remain, and the next time that that antigen is encountered on a secondary response, you get a whole bunch made very quickly of that antibody. And that's why you're immune. That's one of the reasons you're immune. There are T memory cells and there are T B memory cells that remain in tissue, and they can respond more quickly and much more, with a much greater amplitude on subsequent exposure to antigen. And that's why you get a booster of an injection, of a vaccination. It's just your, kind of bump that a little bit, keep it going, keep that titer going. Because over time, as you age, titer levels will fall off. My B memory cells from something I encountered, at your age are just, you're like, oh God, really? Just get sick and die. We're tired. I don't care. That kind of goes off. But that's why it's good to be in the world at large. You keep encountering stuff. That's why you don't get as sick when your kids come. They go to first grade. You got sick with everything in kindergarten, but you're starting to build up some immunity, and so are they. You get sicker, by the way. That's just a little thing. And with your patients, the more you get exposed to your patients, you keep boosting that memory. Antigen recognition diversity, just a little thing there. We only have about 300 genes that produce receptors for antigens, but we can recognize billions, millions if not billions of antigens based on just those genes. And it's really amazing that there is actually rearrangement of genes. This doesn't really, we're probably going to find out that it happens more often, but this is really unique to lymphocytes, that DNA gets deleted and rearranged so that you're making a whole new diversity. So you're making new combos, like that sonic, like all the different things you can, you make all these new combos. And so that is happening through DNA kind of really deletion early on. Neonatally, or I guess fetally even. So just as a little thing to just keep you remembering that is amazing. It's freaking amazing. It's a little bit amazing. What do antibodies do? They attach to antigen. So remember, the B cell is just sitting here going, make an antibody. And so the antibodies go out, and what do? They just stick to the antigen. And what does that do for the antigen? Well, it depends on where that antigen is sitting. If that antigen is something soluble, like a virus, just soluble, the antigen can just bind up soluble, the antibody can bind up soluble antigen and it's neutralize it. And so it's just out there neutralizing it. You can build these big immune complexes where antigen is being attacked by lots and lots of antibody, especially if it's IgM. You can imagine that you just begin to have snowflake clusters of antibody and antigen. Those are called immune complexes. When you have a whole lot of those, they can lodge in the kidney, and then you have glomerulonephritis and those kind of basement membrane destructions, and you end up with protein in the urine. So that's one example of a deleterious thing that can happen. But largely, IgE is going to be the antibody, and it will just neutralize soluble antigen like virus. Okay, what if that antigen is sitting on a cell surface? Oh, well, here's another thing that can happen. Let's say you do, well, wherever that antigen is, soluble or on a cell surface, you can increase phagocytosis by coating that bacterial cell with antibody. Because phagocytes, see how this is so all interconnected? Phagocytes can actually bind this portion right here of the aminoglobulin molecule. This is called the FC portion. This phagocyte can bind that, and it just helps it phagocytose that organism. So if you coat, see these little pictures, if you coat that antigen with antibody, it enhances phagocytosis. That process is called opsonization. Phagocytosis will happen. You can enhance it with antibody. And you see, then that rubs it up. But it's also a way of sticking. All that antibody does is sticks to the antigen. The antibody itself does not destroy the cell bearing it. It's just a flag. That's all it is. And it can flag that thing for phagocytosis. That's pretty clear. We sure think a lot of antibody. Obviously, it's super effective, but in and of itself, it has to have the assist. All it's doing is showing up to the game. The other thing that can happen is it can activate complement cascade. Now, have you heard of complement? Have you had to learn the complement cascade? Have you dreamed about it in a bad sort of way where it looked like Tetris? So, if you have antibody there, the complement cascade can be stimulated by the presence of the antibody. The complement will then poke holes in that cell membrane. So again, the antibody is acting as a flag for the action of something else. Complement, which is a series of proteins produced by the liver that circulates in blood. They are only activated to form the hole that it will form in the surface of the cell if antibody is there to really kind of get it going, for the most part. And so a hole will be poked in that cell very nearby where that antibody is stuck to the antigen. And that one hole might not do anything, but if you coat that with that, say, Staphylococcus aureus with antibody, you get a whole bunch of complement going on it. It can really blow that cell up. And then it's happening on all those cells. So that's cute. And then also you have T cells coming in and doing something really similar. So it's an attack. So here's a summary of antibody action. I have just a little bit more to do. You guys don't have anything until 1, so bear with me. So here's just a little summary. What do antibodies do? They're produced by B cells upon stimulation from antigen-presenting cells plus minus T helper cells. They sit there and just produce antibody, which circulates and sticks to the antigen. That's either a soluble antigen or it's on the surface of something. It enhances opsonization, or it enhances phagocytosis, which is known as opsonization, and it neutralizes soluble antigen, and it stimulates complement cascade. All those things really will work to destroy the cell that was bearing that antigen. Typically, that will be a bacterial cell. Antibody is particularly good against soluble virus and bacterial cells. It's T cell immunity, specifically T cytotoxic, that's going to be really good against intracellular pathogens, funguses, viruses that are intracellular, viruses that have already infected the cell, transplanted tissue, parasites. Do you see how that's different? The immunoglobulin is going to be good specifically against bacterial cell and soluble virus. The T cell immunity is going to be good against infected cells. So cells that look like human cells but that are infected with something else. Because, think about that. Let's say this is a virally infected cell in lung tissue. How is that going to get phagocytized? That's going to be difficult because if it's in your sheet of epithelium or endothelium, then it's going to be better if a T cytotoxic cell or a natural killer cell comes right up to that cell surface and kills it. So the bacteria are going to be soluble in solution as well as viruses, and those are going to be accessed by immunoglobulins. So anyway, it's just me trying to tell you that we can come at anything. And you first have chemical and physical barriers, then you have phagocytosis, and then phagocytosis will act as to present antigen and stem or gem up these arms. of the immune system, and everything really gets needed. And then it gets suppressed as the stimulation goes away. Those things get suppressed, plus T suppressor cells can kind of downregulate it, and then you continue to have B memory and B and T memory cells in tissue, which then allows for immunity. Why do you not have immunity against a rhinovirus, but you do have immunity against something like, gosh, it seems like you get so many illnesses over and over again, but chickenpox, why does the vaccine for chickenpox work? It's because the varicella virus isn't really changing or morphing very much. So you can recognize it because you memorize it. Why do you keep getting the flu? Because the flu virus morphs and changes, and you haven't seen all those flavors yet. Or rhinovirus, you haven't seen all those flavors yet, but you saw varicella, and you recognized it. So that comes from memory. So briefly, I'll just mention superantigens. You'll hear about superantigens. They're just antigens that seem to really super stimulate the immune response. And so with that, you can have concomitant inflammatory damage. So certain organisms really have a lot of, and because, for example, if it's strep pyogenes, you kept getting strep throat because strep pyogenes had a lot of strains, and its cell surface didn't always look the same, and it had a lot of stuff on the cell surface. So if there were 90 things and you can only recognize 45 of those things, then it's super antigenic. You know, so it's able to really evade. And those are the organisms that are difficult to treat, and they've also seen lots of antibiotics, and they've shifted, and so they can evade not only immune response but antibody treatment as well. So that's the word superantigen. It's kind of one of those, it's been popular at certain times. I don't know why I had that slide in there. So just to discuss the immunity and what that means is that there are two forms of immunity. It can be natural immunity or it can be acquired immunity. Natural immunity is what you think it would be. This is you going about your world, being exposed to a variety of antigens, their inhalation, ingestion, contact, and that your body is able to sort of seize them and mounts a response to them, and there are memory cells remaining so that you have immunity to any subsequent exposure. You're born with it. You're born with the ability, your natural ability, or natural passive immunity. I should say natural active immunity is you just getting exposure. Thanks for your exposure. Natural passive is that you're born with a certain amount of IgG that can cross the placenta, so your maternal IgG would be natural passive immunity. And then breastfeeding also provides for natural passive immunity, giving you immunity in the form of, and here we're really following immunoglobulins because we can test for those. We can't test so well for T cells, but we can test for a titer of immunoglobulins. That's why then you assess immunity based on immunoglobulins because there's a lab test for that. So we tend to forget that there is all that cellular immunity that's really super important in getting all that going because you don't test for that. So anyway, when we talk about this, it's about antibody titer. Artificial immunity would be immunity you acquire through artificial means. So artificial active immunity is that I inject the antigen into you and you mount an immune response. Artificial passive immunity would be I inject the immunoglobulins in you. And so artificial active immunity is vaccination. Artificial passive immunity would be injection of preformed antibody. And one of the big ones is if you've been exposed to hepatitis A. That's a big one. You would go get an immunoglobulin shot to kind of cover you in case there was exposure. Viral vaccines. I just want to note, you've probably covered all of this, but you don't have a dead virus because the virus was never alive. This is just a picky point, but it's it's just true. Viruses aren't living. They are not autonomous. They have to have a host cell to replicate themselves. So you can inactivate them, but you can't kill them. So to say a dead virus is really, and I make that point because just understanding that is why it's different to approach the treatment of viral diseases. So they can be non-infectious components that are inactivated. Or it can be a virus that is attenuated, which means it is capable of replication in a host cell, but it has been altered such that it is non-virulent. So it's an effective virus that doesn't kill. Now that's really good immunity. Really good immunity is born by something that can colonize or interact and replicate itself. That's more natural, and so it gets the immune system to get better. Bacterial vaccines can be killed or attenuated. The word attenuated should really be not indented. A bacterial virus can be killed cells or attenuated cells. Quite often are really component vaccines. They're recombinant. So you're just getting antigens, bits of antigens, you're not getting anything cellular. And if it's a denatured toxin, we call it a toxoid. So diphtheria toxin is a toxoid vaccine. Tetanus toxin is a toxoid vaccine. And then there's just, I don't care that you have to know this for other stuff, but just to show you what some of the vaccines, they come in all of those flavors. And then obviously the recombinant ones. Here's just to remind you, there was a vaccination schedule. Do you remember that from pediatrics? Also geriatrics, vaccination schedule. We got that for Univax especially. So anyway, just to remind you that you had that, and that should be mentioned during infectious disease. Future vaccines. Nothing is more stimulatory than having really encountered something that's replicating in the body. And so is inserting a protein from whatever agent into a plasmid and treating it as a vector that can then go in. And this is probably how recombinant drug therapies will work. And the feature is let your cell make the thing. So anyway, you'll see lots of changes going on. Okay, so my ex-husband is Jewish, and so I was not exposed to the Talmud or the Jewish Book of Laws, but he had this, his mother had given him this quote, and I always thought it was so lovely, but it's from the Talmud. Whoever saves a life, it is considered as if he saved the entire world. So nothing is petty that you will go do in your lives. Nothing is little that you go do in your lives, and the people that you encounter, they will wear you smooth out. But they're suffering, and they come to you, and you will offer them something. And your reservoir will refill because it's important. And I just always loved that from the Talmud, and I appreciated being exposed to Jewish things, all things Jewish. Just stuff like Jesus, stuff that Jesus saw. I love that. Okay, so here are a couple of wedding pictures before dinner. Yes, she wore Converse. Those are Jack Purcell's. That's your thing. Okay. There's this first look as a thing now. They didn't want to do that, so they did a first prayer. So they were just around the corner with each other, and he's just bawling his eyes out. He's the sensitive one. She's like a rock, I would say. I mean, she was like a 5-year-old. I'd be like, going, what is there in there? Because there's no soul. She's very rocky. She's very stoic, and he's just